Hi, this is Dr. Anthony Revis with SVSU, Gen Chem 111, Chapter 10, on the topic of intermolecular forces, Lecture 1 of Chapter 10 on intermolecular forces. In this chapter, we will look at intermolecular forces, properties of liquids, phase transitions, phase diagrams, the solid state of matter, and we will also look at lattice structure in crystalline solids. When we examine these topics, we will look at them, but not necessarily in this order. Also, Chapter 10 is taught as a survey overview of the topics than an in-depth discussion. So let's get started with Chapter 10, Intermolecular Forces. So let's start to talk about intermolecular forces. Intermolecular forces are attractive forces between molecules. They are the sum of all the forces between neighboring molecules. In other words, the interactive forces between molecules are what we call intermolecular forces. These are not the forces within the molecule itself, but these are the forces and interaction that the molecule experiences by interacting with other molecules. And they take into account all the different types of forces as they interact. There are four basic types of intermolecular forces, or four names for intermolecular forces. Ionic forces are one of those types. Ionic forces are interactions between charged atoms. So when the atoms are charged, they have ionic forces, or they experience ionic forces. And it's those ionic forces that help them form some type of intimate interaction. There's also hydrogen bonding. Hydrogen bonding occurs in molecules that have hydrogens attached to atoms that causes them to be more polar. For example, a hydrogen attached to an oxygen or a nitrogen or a sulfur might make it more polarized. Therefore, it tends to carry a partial positive charge, and that hydrogen with the partial positive charge undergoes hydrogen bonding. Then there are two types of van der Waals forces: dipole-dipole interactions and dispersion forces, which are also called London forces. Dipole-dipole in many ways are like marbles bouncing against each other. Dispersion forces are like molecules that will acquire a momentary polarized region. We will survey these forces as we work our way through this chapter. Now, it is important to note that the phase in which a substance exists depends on the relative extent of its intermolecular forces and the kinetic energy of its molecules. In other words, when we look at a solid, there are certain intermolecular forces that are responsible for it being in the solid phase. And there is a certain amount of kinetic energy involved in a solid. That kinetic energy and the strength of the intermolecular forces are different when it's in the liquid phase. It is in the liquid phase because of its intermolecular forces and the kinetic energy of the molecules in that liquid phase. Likewise, the intermolecular forces and kinetic energy of a gas is different from that of a liquid, which is again different from that of a solid. In going from a solid to a gas, there is an increase in the kinetic energy that occurs also when there's an elevation in the temperature. Intermolecular forces, however, are stronger in the solid phase than in the gas phase. So, kinetic energy increases with temperature. Intermolecular forces increases with a decrease in temperature. In the gas state, we have a higher degree of kinetic energy. In the solid state, we have less kinetic energy. In the solid state, we have stronger intermolecular forces. In the gas phase, we have weaker intermolecular forces. Again, intermolecular forces are attractive forces between the molecules. Keep that in mind. They help the molecules to come together. They are a binding force between there. They're not permanent bonds, but they have a strong interaction that helps the molecules to come together and stay together. That differs from intra, TRA, molecular forces. Intra involves the forces within the molecule itself. We show you a diagram here where, for example, you have chlorine and an H bond. The intramolecular forces would be very strong in the HCl bond. However, the intermolecular force would be weaker between the two molecules. And the alignment of that molecule will involve the hydrogen, because it's partial positive, aligning with the partial negative chlorine atom. But those will be intermolecular forces, and although they may have a certain strength, that strength does not match the strength of a permanent covalent intramolecular bond, which has the intramolecular forces. Okay? So, in general, intermolecular forces are much weaker than intramolecular forces. There are ways to measure or get an indication of what the intermolecular forces might be, and there are several physical property results because of the intermolecular forces. For example, boiling point, melting point, heat of vaporization, heat of sublimation, heat of fusion. These are all the result of intermolecular forces. These are physical property manifestations of the intermolecular forces. So boiling point, melting point, they're all related to the intermolecular forces. So, to recap it, intramolecular forces keep molecules intact. They keep the molecule as a molecule. Intermolecular forces hold multiple molecules together and determine many of the substance's physical properties. So many of the properties of the material, of the compound, of the molecule is determined by its intermolecular forces. The fundamental chemical properties are, for the most part, determined by the intramolecular forces. Okay? The intermolecular forces tend to result in indications of the molecule's physical properties. So you want to keep that little bit of a hint in mind. That is another way to think about inter versus intramolecular forces. Intramolecular forces require destructive methods to separate that force. Intermolecular forces can be separated by physical means. So let's talk about dispersion forces. What are dispersion forces? Attractive forces that arise as a result of temporary dipoles induced in atoms or molecules are dispersion forces. In other words, we've talked about dipole, we've talked about dipole moments. We know that a dipole is a polarization of the electrons. It occurs when one side of the molecule or one atom in the molecule attracts most of the electron density, attracts most of the valence electrons in the molecule to its side, making it electron rich and leaving the other side electron poor. In doing so, a positive negative charge builds up on the electronegative side of the molecule, and a positive charge is left remaining on the electropositive side of the molecule. So, dipole-dipole forces attract forces between polar molecules. Okay? So this is a type of dispersion force. A dipole-dipole force is a dispersion force. The dipole-dipole force are responsible for attractive forces between polar molecules. So the attractive force between polar molecules is a dipole-dipole force. So we can have these dipole-induced dipole interactions where we have a dipole and exactly what it sounds like, a dipole. It's essentially bipolar. It has a negative and a positive pole. Although it is not permanent in the molecule, it is induced because of its interaction or its proximity to other molecules. And its proximity to those other molecules causes it to acquire an induced dipole. So again, it's not permanent, it's simply induced. And when it's induced, we get dipole-dipole forces. Another type of dispersion force is an ion dipole force. Okay? In an ion dipole force, attractive forces between an ion and a polar molecule occur. So if you have an ion and you have a polar molecule, it's called ion dipole force. And simply by the names, you know what it means. You see ion dipole, that means one part is an ion, the other part is a polar molecule. If you see dipole-dipole, it simply means you have polar molecules that have an induced dipole because of this interaction or proximity to the other molecules. Okay? So, an ion dipole is an attraction between an ion and a polar molecule. Paying attention to the sign, the plus or minus sign, can help you align the interaction so that you can see the type of interaction it is, whether it's polar molecules or ion polar. So you have plus going to minus, plus, minus, plus, minus. Okay? So you want to keep that in mind. So, dispersion forces are usually dominant of the three van der Waals forces. There are three types of van der Waals that we can think about. The orientation, there's van der Waals due to its orientation. Then there's induction and dispersion. So, dispersion forces are usually the ones that dominate the three. Okay? And that's usually the case except in molecules that are small and the ones that are highly polar, like water. Okay? Otherwise, dispersion forces tend to be very, very strong forces. So, dispersion forces are very strong interactions in many molecules. It's interesting to note that heavier molecules and atoms exhibit stronger dispersion forces than lighter molecules and atoms. That is a trend that you will want to retain. Heavier molecules and atoms exhibit stronger dispersion forces than lighter molecules and lighter atoms. The reason for this is because larger atoms have greater polarizability due to the valence electrons being further from the nucleus. In other words, the larger the atom is, the further down the periodic table the atom is, the larger the N value, the larger value is, it tends to be more polarizable. In other words, there is a higher degree of separation between the partial positive and the partial negative charge. Okay? So what is polarizability? The measure of how easy or difficult it is for another electrostatic charge to distort a molecule's charge distribution is called polarizability. In other words, polarizability just looks at how likely or how strong does one atom force the induced migration of electron density in its direction. So you want to be aware of that. So that's what polarizability is, and there are several factors that go into it. We will not, in this lecture, go into that level of detail. So suffice it to say that larger atoms tend to be more polarizable. Okay? Because they're lower down on the periodic table, which means that their valence electrons are further from the nucleus. In other words, the larger the atom, the further away from the nucleus it is. Okay? We show you a diagram here where we see the unequal distribution due to polarization. We see the partial negative taking on more electron density than the partial positive. And we have this attractive force of plus to minus that's induced, and it's a temporary dipole. It is not permanent. It is a temporary dipole that is induced because of its proximity to the other molecules. So dispersion forces result from the formation of temporary dipoles, and that's important to note. So where do dispersion forces come from? They come from temporary dipoles. When a temporary dipole is formed, we get dispersion forces. The degree of polarizability and the extent of dispersion forces within a molecule result in certain physical property features. We show you here melting point, for example. Melting point of similar nonpolar compounds are shown in this particular diagram, this particular slide. Note we have methane, and we take methane all the way to carbon tetraiodide. Note that we start with hydrogen near the top of the periodic table, or at the top of the periodic table, and we take this series through to I, which is near the bottom of the periodic table. You can find these halogens in group 17 on the periodic table. Note that in going from hydrogen through iodine, the melting point increase. That's because as we get to iodine, iodine is a larger atom, and therefore it's more polarizable because the valence electrons are further from the nucleus, are further from the influence of the positive protons in the nucleus. Okay? So note again that the melting point with I4 is higher than B4, which is higher than CO4, higher than F4, higher than H4. This is because the dispersion forces are different in each of these molecules. And because they are different, the physical properties are different as well. Polarizability has a strong influence on the dispersion forces. That is a key principle that you will want to retain. Okay? So let me say that again. Polarizability has a strong influence on dispersion forces. The greater the polarizability of the atom, the higher the dispersion forces. The higher the dispersion forces, the higher the melting point. atoms near the bottom of the periodic table will be more polarizable than atoms near the top of the periodic table within the same group. So, stronger dispersion forces lead to higher melting and boiling points. So not only does the melting point increase, but the boiling point increases. Higher temperature and therefore more kinetic energy is needed to overcome the intermolecular forces. So we show you here a table, shows the molar mass, and shows the atomic radii. And as the atomic radii increase, you note the melting point and the boiling point increases. The atomic radii increases as we go down the periodic table. So you want to be aware of that. And so we show you these halogens and the effect that it has. It is directly proportional to molar mass, but the key contributor is its polarizability also increases. So the polarizability increase within this halogen group from top to bottom. And we note that there's a melting point increase, boiling point increase, radii increase, or at least radius increase, and the molar mass increase. There are other features that affect dispersion forces. For example, the strength of the dispersion forces also increases with increases contact area between molecules. This is an important feature to make note of. In other words, the more contact points molecules have in an intermolecular fashion, the greater the dispersion forces. Okay? So we get stronger dispersion forces when there's more contact. So it's like thinking of more sticky points, even though many of these molecules are not really that sticky. But it's the difference between stacking chairs in a uniform fashion versus simply randomly stacking in oddball chairs. You can stack more chairs if they're uniform chairs and all the same type chairs. If they're random chairs or someone puts a chair in a little off, you can't stack anymore. The better the contact, the more intimate the contact, the greater the dispersion forces. So, let me repeat it. The strength of the dispersion forces increases with increasing contact area between molecules. Show you examples here, and you can tell this by the boiling points is one way that you can measure it. If we take a look at these pentane isomers, we take a look at them, we note that neopentane has a boiling point of 9.5. That's because it's in somewhat of a ball. Fewer contact places. Isopentane has a few more at 27 degrees C, but then normal pentane, the straight chain, has more. In other words, straight chain pentane can stack better. Isopentane, which stacks better than the neopentane. That is an important principle to note, that higher contact area increases the dispersion forces, which increases the boiling point. So, even though these molecules have the same chemical formula, the difference in boiling points suggests that dispersion forces in the liquid phase are different. And because those dispersion forces are different, we have different physical properties for these isomers. So let's review some principles by practicing some problems. What type of intermolecular forces exist between the following pairs? We have the pairs and we have the solution for you. And we're going to talk through them to help you to understand and review the concepts about intermolecular forces. Okay? So we have HBr and H2S. We inspect the molecules and we start to think about the principles. And here's what we find. Both HBr and H2S are polar molecules. We know they're polar molecules because we can draw out the Lewis structures, and we note that the Lewis structure of HBr has lone pairs around the bromine. You know how to draw a Lewis structure, and it's polarized towards the bromine. We note that H2S has two lone pairs on it, and you know how to draw those lone pairs, and the molecules are therefore polar. Therefore, the intermolecular forces present are dipole-dipole forces as well as dispersion forces. Okay? So these are the two forces that result from their composition and from an understanding of their Lewis structures. Chlorine, Cl2, and CBr4. By the way, I point out the atoms individually this way so that you can focus really on the atoms. The atoms is what matters when we do this. So we have Cl2 and CBr4. Both Cl2 and CBr4 are nonpolar. We know they're nonpolar in the case of chlorine because there are no polar bonds. Therefore, it is by default nonpolar. We know that CBr4 is nonpolar even though it has polar bonds. The CBr bond is polar. It's polarized towards the bromine. However, we have four of those that are equally polarized in that direction. It is a tetrahedral shape. Therefore, all four of the polarized bonds cancel out. So they're both nonpolar. So, there are only dispersion forces between these molecules. In other words, when the molecules are nonpolar, dispersion forces are what we expect to see. Let's take I2 and NO3 minus. I2 is a homonuclear diatomic, meaning that it's a diatomic in its natural state, and it's a diatomic with the same exact atoms, and therefore it is nonpolar. We get that because, again, they're the same atom. So, the forces between it and the ion are ion-induced dipole forces. In other words, it's clear that NO3 is an ion. We see that because it has a negative charge. And we know that I2 is nonpolar. Therefore, we expect the ion to induce a dipole in the nonpolar molecule. Okay? NH3 and C6H6. NH3 is polar. We know that it's polar because if we draw the Lewis structure, we find that there's a lone pair on the nitrogen, and because of that lone pair, we have polarization in that direction away from the hydrogens through the nitrogen in the direction of the lone pair. And we know that C6H6 is nonpolar because it has an equal pull in the direction of carbon for all six of the hydrogens. The forces are dipole-induced dipole because we have this polar and nonpolar. So therefore, we have dipole-induced polar forces and dispersion forces. So we have a combination happening here. You will want to take a look at these and practice through it. These are the types of questions that one might expect from this subject matter. Let's talk now about hydrogen bonds and hydrogen bonding. The hydrogen bond is a special dipole-dipole interaction between the hydrogen atom in a polar, meaning NH, OH, FH, for example, bond, and an electronegative O N, or F atom. So when we have nitrogen that has an H on it, O with an H, F with an H, you can expect or at least start to look for the potential for hydrogen bonding. And certainly if there's an oxygen or nitrogen fluorine around, it will do that. These molecules will interact within themselves to do hydrogen bonding. So you want to be aware of that. So here are examples. Water. Water will undergo hydrogen bonding with itself. The H is a partial positive. The oxygen is partial negative. Therefore, we would get an interaction shown in this slide in the red dots, and that's hydrogen bonding. We can also get hydrogen bonding in NH3 and ammonia. So how do we get that? Well, we have the lone pair on the amine. That lone pair is polarized towards a partial negative, and it will seek out a partial positive from the hydrogen on itself, on the amine. And therefore, it would be polarized in such a way that it undergoes hydrogen bonding. You can also have hydrogen bonding between the water and the amine. In fact, this is why these materials tend to be soluble in each other because of the hydrogen bonding. So, you want to look at this and remember that electronegative groups that have hydrogen on them will have the potential to undergo hydrogen bonding. The ones that you absolutely don't want to forget are hydrogen and ammonia. You can expect these to undergo hydrogen bonding within itself and with each other. Water molecules participate in multiple hydrogen bonding interactions with nearby water molecules. So water is basically a network of hydrogen bonds. And because we have this network of hydrogen bonds, it gives a boiling point of 100 degrees C. Hydrogen bonding tends to increase the boiling point of compounds. So if you have a compound of similar molar mass or similar structure, similar composition, and one has OH and the other one does not, the one with OH will generally have a higher boiling point because of the hydrogen bonding that it undergoes. Again, water molecules participate in multiple hydrogen bonding interactions with nearby other water molecules. When it does it, it builds up this 3D structure of water, where it's simply a network across network across network across network of hydrogen interacting with partial negative oxygen, and then again partial positive hydrogen interacting with partial negative oxygen over and over again, and it builds up a network, and that network causes hydrogen to have the boiling point that it has. It might be of interest to also know that the citric acids or the acetic acids or the fruit acids also undergo hydrogen bonding because they contain a carboxylic acid group. Now, water will also interact with cations. Okay, we show you here an example of sodium plus cation, and then we have a magnesium plus 2 cation, and those cations interact with the partial positive negative on the water molecule to produce an intermolecular force of the cation with the water molecule. And we show you what these cations will look like in solution. So when we talk about this, we will essentially say that water solvates or surrounds the cation by interacting with the partial negative charge on the oxygen and the positive cation on the metal. And in this case, the metal is sodium and the other metal is magnesium. Okay? The strength of the interaction is proportional to the size of the charge. Okay? The charge that is on the cation. All right? So, sodium has a +1. Magnesium has a +2. Magnesium will have a stronger interaction than the sodium because the magnesium has a +2. Okay? These type of interactions are what cause hard water results in your city water or your tap water. So what's happening is the water molecule is interacting with cations in your water supply. And we call it hard water. So let's talk now about some more of the physical properties of water. If we take a look at a density versus temperature curve for water, we find that about 1 gram per mil or 1 gram per cc or 1 gram per cm cube, we find that's where the maximum density is achieved for water. So at about 1 gram per mil, we get the maximum density of water. That's the bottom line. Okay? So be aware of that. About 4 degrees, we find its maximum. Therefore, that is the density of water. Okay? We note that the boiling point of water is about 100 degrees C. Both these properties are related to its hydrogen bonding. Ice is less dense than water. It has a density of 0.92. Okay, and that's important to note. And it melts at 0 C. It is unusual for solids to have lower densities than the corresponding liquid phase. Why is that the case for water? Well, water reaches its maximum density as a liquid rather than as a solid like other liquids. Why? Here's why. As water freezes, the hydrogen bonds don't allow it to compress like other freezing liquids. In other words, the structure of the hydrogen bonding network in water does not allow the water molecules to collapse and become more tightly packed while it's freezing. Therefore, its volume is larger as a solid than as a liquid. That is the unusual feature. Okay? The mass is the same. The mass does not change. But its volume is larger as a solid than as a liquid, which is typically not so for liquids. So, since density is mass per unit volume of the material, the density of ice is less. That's why ice floats, by the way. So, in other words, in the case of water, we have the same mass divided by the volume. However, when we freeze the ice, the volume increases, and you know mathematically what happens when the denominator increases. Yeah, your answer gets smaller. And that's what happens. And that's one of the interesting features about the hydrogen bonding within water. Its structure doesn't allow the water to compress or the molecules to get as tight and more as intimate when it freezes, and therefore it has a higher volume many other liquids when it freezes. Okay? So you want to be aware of that. So these are the physical properties of water, and those physical properties are related to the intermolecular forces present in the water molecule. So with that, let's take a look then at density. Density compares the mass of an object to its volume. It is the mass of a substance divided by its volume. So you have mass over volume to calculate density. This is one of those formulas you memorize and you hang on to it the rest of your chemistry career. So density equals mass over volume. We show you some examples of densities in this slide. We have a quark at 0.26 gram per mil, all the way up to gold, which is 19.3 gram per mil. By the way, this is how the jewelers know whether or not you have gold versus something else that's plated many times. They just check the density. So they run a density calculation on it, and right away they tell you, nope, this isn't pure gold. The density will tell right away. So body fat's about 0.9 gram per mil. Again, it's gram per mil or gram per cc or gram per cm cubed. Okay. Note that gasoline has a density of 0.74 and mercury is 13.6. Then we have things like hydrogen is very, very low density. This gas, hydrogen, is 0.09. Gases don't have a very high density at all. And here we show you examples here for hydrogen gas and helium. But then as we go up, we find dry air now gets about 1.29. And carbon dioxide gets up to about 1.96. So we have a variety of densities shown here for different types of compounds. And they're all calculated based upon mass over volume. Or at least they are the result of their mass per volume. Okay? So the result of the mass per volume is what's called density. So before we return to our discussion about intermolecular forces, let's practice a density calculation. Okay? Again, we know that density compares the mass per volume. So let's practice it. A 0.258 gram sample of high density lipoprotein has a volume of 0.215 centimeter cubed. What is the density of HDL sample? We take the grams, we divide it by the volume, and we punch the numbers through, and we get the answer. Okay? That's how we do it. It is that straightforward. Mass over volume. Don't second guess it. That's how we do a simple density calculation. Let's just practice one more density calculation that might involve a laboratory experiment. In the figure below, the water level rises from 35.5 mils to 45.0 mils after the zinc object is added. What is its density? This is an example of doing density by displacement. The water displacement tells you the volume that metal occupies. Okay? So, the density will equal to the mass of the zinc, which we read from the scale at 68.60 gram of the zinc, and the water displacement is by difference between the two water levels, which is 9.5, and we calculate it through and we get 7.2 with 2 sig figs because we have 2 sig figs in the volume. So this is an example to show you how to calculate the density. But the density is the result of its intermolecular forces. So let's return to discussions about intermolecular forces, and let's talk about some more physical properties of liquid. Let's talk about viscosity. What is viscosity? Viscosity of a liquid is a measure of its resistance to flow. So how well it resists the flow is viscosity, and you intuitively know this. Something that drips off very slowly has a higher viscosity than something that simply drips off right away. As the temperature increases, the viscosity of the liquid decreases because of increased kinetic energy. Okay? So, kinetic energy is an important concept to think about when we think of these physical properties. And it is very evident in viscosity, the impact of kinetic energy. Increase the temperature, your honey flows better. Okay? So that's viscosity. The resistance of flow is viscosity, and there's several units that viscosity might be measured in. It goes from industry to industry. We're not going to go into detail on how we derive these units, but suffice it to say that there's several different units for viscosity, and we show you some examples here for this where we have the. So what we really want you to do is see the relative values here. We're not going to go into any more detail than that, but just notice that water starts very thin and motor oil gets thicker, and honey is somewhere near the top of the chart for these. So we have water and then we have honey, and you can think about it that way. And you know the viscosity of honey is much greater than water, and then motor oil is less than honey. Okay, and then you have these syrups somewhere in between there. So the bottom line is the materials that flow less have higher viscosity. That viscosity is because of the intermolecular forces that exist within that molecule or within that composition. Okay? So be aware of that. I'd like for you to note ethylene glycol here that we have is an alcohol, an OH, therefore it's going to have hydrogen bonding in it. One of the things you might try doing or practice doing is take each of these and decide what type of forces you think might predominate in these molecules. Okay? So there's an exercise for you all your own. So that's it for viscosity. Let's talk next about surface tension. What is surface tension? Surface tension is the amount of energy required to stretch or increase the surface of a liquid per unit area. In other words, surface tension is the energy that it takes to spread a drop. You put a drop on something, how fast does it spread? How well does it spread? That's an indication of surface tension. For example, that's why water beads up on certain surfaces and doesn't bead up on others, because the one it beads on has a higher surface tension, meaning that the drop will not wet that surface, and since it will not wet that surface, it beads up. And that is surface tension. Okay? And one of the ways that they measure the surface tension, or that they use to judge the degree of wetting, is by the contact angle. Okay? So be aware of that. That's just information to know that you have a sharp contact angle versus a wide contact angle. It indicates the degree of wetting and the degree of surface tension. And surface tension is a result of intermolecular forces. Okay? So, if we have strong intermolecular forces, we get higher surface tension. That is a take-home principle. We show you the units that this measured in for surface tension. They're shown here. You can play with this, take a look at it. The real key is to note that surface tension varies based upon the intermolecular forces. And that's the important principle that we want you to remember. So surface tension is influenced by intermolecular forces. Okay? That's an important principle to take home. All right? So there you have it. Chapter 10, Intermolecular Forces, Lecture 1. That's Lecture 1, Chem 111, Chapter 10.